Modulation schemes in Ethernet. Ethernet primarily uses pulse amplitude modulation, PAM, evolving from simpler schemes like NRZ, PAM2, for basic data to more advanced PAM4 for high speeds, 100G/200G/400G, encoding 2 bits per symbol for greater bandwidth efficiency, alongside older methods like MLT3 for 100 base TX and OK, on-off keying, in optical links, all designed to map digital data onto physical signal characteristics like voltage or light pulses for transmission. Key Ethernet modulation schemes. NRZ, non-return to 0/PAM2, the simplest form, using 2 voltage levels, high/low, to represent ones and zeros, effective for shorter distances but limited in data rate. PAM4, 4-level pulse amplitude modulation, uses 4 distinct voltage levels to encode 2 bits, 00, 01, 10, 11, per symbol, doubling the data rate for the same symbol rate compared to NRZ, crucial for modern high-speed Ethernet, 50G/100G/200G/400G. MLT3, multi-level transmit 3, used in 100 base TX, fast Ethernet. It cycles through 3 voltage levels, -1, 0, +1, to transmit data, reducing electromagnetic interference. OK, on-off keying, a form of amplitude shift keying, ASK, where light is either on, 1, or off, 0, used in optical Ethernet like 100 base FX. How they work. 1. NRZ/PAM2, a high voltage means 1, a low voltage means 0. 2. PAM4, 4 voltage steps, example -3V, -1V, +1V, +3V, allow each pulse to carry 2 bits, significantly boosting throughput. 3. MLT3, 401, it changes to the next level in the sequence, -1-0, 0-1, 1-0, staying put for a 0. Evolution and choice. Higher speeds, like 200G/400G, demand more complex schemes like PAM4 to overcome bandwidth limitations and channel losses, as shown in the Signal Integrity Journal article. The choice depends on speed, distance, and physical medium, copper versus fiber, balancing data rate, spectral efficiency, and implementation complexity. Ethernet utilizes various modulation schemes depending on the transmission medium, copper or fiber, and the required data rate. The primary schemes employed are pulse amplitude modulation, PAM, in its various levels, PAM2, PAM3, PAM4, PAM5, PAM16, and, for early standards, non-return to 0, NRZ, signaling. Common Ethernet modulation schemes. Ethernet speed medium modulation scheme. Standard 10 base T 10 Mbps twisted pair. Manchester encoding 100 base TX 100 Mbps twisted pair. MLT3, over 2 pairs, 100 base T1 100 Mbps. Automotive PAM3 4D. PAM5, uses 5 voltage levels across 4 1000 base T1 Gbps twisted pair. Pairs, 2.5G/5 base T 2.5/5 Gbps twisted pair. PAM16 with gray coding 10 base T 10 Gbps twisted pair. PAM16, Tomlinson Hiroshima Precodet, THP, 40G plus Ethernet 40 Gbps and up fiber/copper. PAM4, most common for modern high-speed, key modulation types. Pulse amplitude modulation, PAM, the most prevalent technique in modern Ethernet, especially for high speeds over copper and optical fiber. Information is encoded in the amplitude of a series of signal pulses. NRZ, PAM2, the traditional binary scheme using 2 voltage levels to represent 0 and 1. It was used in early Ethernet standards. PAM4, uses 4 distinct amplitude levels to represent 2 bits, 00, 01, 10, 11, per symbol. This effectively doubles the data rate for a given bandwidth compared to NRZ, making it ideal for 40G, 100G, 400G, and 800G Ethernet links. PAM5, uses 5 voltage levels, notably in gigabit Ethernet, 1000 base T, allowing efficient use of all 4 twisted pairs simultaneously. PAM16, used in 10 base T, 25G, and 50G base T standards, it employs 16 discrete amplitude levels to encode data. Trellis-coded modulation, TCM, often used in conjunction with PAM schemes, like in 1000 base T and 10 base T, to improve error performance without increasing bandwidth or transmit power. Other schemes, Manchester encoding, an early method for 10 Mbps Ethernet, 10 base T, where data is represented by voltage transitions rather than levels, which helps with clock recovery and electrical isolation. Carrierless amplitude phase, CAP, used in some older or proprietary systems, it is a single carrier system that is simpler than OFDM. Quadrature amplitude modulation, QAM, while less common in standard twisted pair Ethernet, it is used in some specialized applications and long-distance coherent optical systems, as it employs both phase and amplitude modulation. The shift toward higher-order modulation schemes like PAM4 is driven by the need for higher data rates without requiring a proportional increase in physical channel bandwidth, though it necessitates more complex circuitry and stricter signal-to-noise ratio requirements. PAM4 in Ethernet. Pulse amplitude modulation 4-level, PAM4 is an advanced signal modulation technique that has become essential for achieving high data rates, 100G, 200G, 400G, 800G Ethernet, and beyond, in modern data centers and communication systems. It is a significant evolution from the traditional two-level non-return to zero, NRZ, modulation scheme. How PAM4 works. PAM4 encodes data by using four distinct signal amplitude levels to represent combinations of 2 bits of data within a single symbol period, clock cycle. NRZ, PAM2, uses 2 levels, high/low voltage, to represent 0 or 1, transmitting 1 bit per symbol. PAM4 uses 4 levels, typically mapped using gray coding to reduce errors between adjacent levels, to represent 2 bits, level 0, 2000 level 1, 01 level 2, 10 level 3, 1 by transmitting 2 bits per symbol. PAM4 effectively doubles the data rate for a given channel bandwidth compared to NRZ signaling. This allows network operators to achieve higher data rates, example 56 Gbps per lane, without needing to double the physical channel's bandwidth, which would be 56 Gbaud for NRZ, but is only 28 Gbaud for PAM4. Advantages and disadvantages. Feature PAM4 characteristics. Data rate 2 bits per symbol, doubling throughput versus NRZ at the same baud rate. Bandwidth highly efficient, allowing high speeds, 400G, 800G, to use existing channel efficiency infrastructure. Lower, 9-10 dB less than NRZ, due to the 4 amplitude levels being closer SNR margin together. Requires more complex transceiver designs, including digital signal processing complexity, DSP, and forward error correction, FEC. Generally consumes more power due to the complex signal processing and power equalization needed. Best suited for short to medium reach links, example within a data center, due to distance higher susceptibility to noise and signal degradation. Applications. PAM4 is the backbone technology for modern, high-speed networking standards, particularly in large data centers and high-performance computing clusters. Key applications include Ethernet, mandated in IEEE 802.3 standards for 50G, 100G, 200G, and 400G plus interfaces, both over copper and optical fiber. PCI Express, PCIe adopted by the PCIe 6.0 standard for high-speed interconnections in servers and systems. Memory interfaces, used in graphics card memory such as GDDR6X to achieve high bandwidth. Implementing PAM4 modulation presents several significant technical and operational challenges compared to traditional NRZ signaling, primarily related to signal integrity, system complexity, and power consumption. Signal integrity and noise susceptibility. The most prominent challenge of PAM4 is its reduced noise margin. Because the same voltage range is divided into 4 levels instead of 2, as in NRZ, the vertical height of each eye in the eye diagram is only about 1/3 that of an NRZ signal, leading to a signal-to-noise ratio, SNR, penalty of approximately 9.5 dB. Increased noise sensitivity. The smaller amplitude separation makes PAM4 signals highly susceptible to various impairments, including random noise, crosstalk, and signal reflections. Channel impairments. PAM4 signals are more sensitive to intersymbol interference, ISI, and channel loss. Without careful design and equalization, signal degradation can lead to a completely closed eye diagram at the receiver, making data recovery impossible. Nonlinearity and skew. Nonlinear behavior in transmitters or receivers can cause the 3 eyes of a PAM4 signal to have different heights or be misaligned in time, inter-eye skew, which further complicates signal detection and increases the bit error rate, BER. System complexity and power consumption. To counteract the signal integrity challenges, PAM4 systems require more sophisticated hardware and processing techniques, which introduce their own set of challenges. Digital signal processing, DSP. PAM4 receivers require complex digital signal processing, DSP, for advanced equalization techniques, like FFE and DFE, to open the closed eyes and compensate for channel impairments. Forward error correction, FEC. Due to the inherently higher uncorrected BER of PAM4 signals, FEC is mandatory in virtually all high-speed PAM4 standards, example 400G Ethernet. FEC adds redundant data to correct errors at the receiver, but requires extra processing power and can slightly increase latency. Increased power and cost. The complex circuitry required for DSP and FEC, along with the need for high-performance analog-to-digital converters, ADCs, in the receiver, results in higher power consumption and larger integrated circuit, IC, sizes compared to simpler NRZ systems. This increased power dissipation is a significant concern for data center operators. Testing and measurement hurdles. Characterizing and validating PAM4 links is significantly more complex than NRZ, requiring specialized and high-performance test equipment. Complex measurements. Engineers must perform new measurements for 3 distinct eye diagrams, instead of 1 for NRZ, including metrics like signal-to-noise and distortion ratio, SNDR, and transmitter dispersion and eye closure quaternary, TDIC. Equipment demands. Test instruments need extremely low intrinsic noise and jitter to accurately measure the tight margins of a PAM4 signal, making high-end oscilloscopes and bit error rate testers, BERTs, more expensive and essential for validation. Simulation versus reality. Accurate simulation of PAM4 behavior to predict performance is critical because real-world artifacts and noise can have a greater impact on link performance. PAM4 is used extensively in high-speed Ethernet standards in modern data centers and telecommunications networks, primarily for speeds of 50 Gbps and above per lane. It is a critical enabling technology that allows for increased data rates within existing bandwidth limitations of both copper and fiber optic channels. Key areas of PAM4 use in Ethernet. PAM4 has become the standard modulation scheme for current and next-generation Ethernet speeds, both over optical fiber and electrical traces, example backplanes and short-reach copper cable speed standard, S, examples, medium, S, lanes, per link, IEEE 802.3 CD fiber, MMF, SMF, 50 GBE 1 lane, 50 base SR/FR/LR, electrical 100 IEEE 802.3 CD, 100 base SR2, 2 lanes, or sometimes 4x25G fiber, electrical GBE 802.3 BMNRZ legacy, 200 IEEE 802.3 BS, 802.3 CD fiber. Electrical 4 lanes GBE 400 IEEE 802.3 BS fiber, electrical 4 or 8 lanes GBE, 400 base DR4/FR8/LR8, 800 ongoing standards fiber, electrical 8 lanes, or 4x200G PAM4, GBE 1.6 TBE ongoing standards fiber, electrical 8 lanes or higher. Specific applications: data center interconnects, DCI, and server links. PAM4 is foundational for the spine-leaf network architectures used in hyperscale and AI/ML data centers. It is widely used in pluggable optical modules like QSFP-DD and OSFP form factors for speeds of 100G, 400G, and 800G. Electrical interfaces, SerDes and backplanes. PAM4 is the primary signaling method for high-speed serializer/deserializer, SerDes, lanes within networking equipment and across server backplanes, operating at speeds of 50G, 100G, and 112G per lane. Copper cable assemblies, direct attach copper, DAC, cables for 50G, 100G, 200G, and 400G links within racks also utilize PAM4 signaling. The shift from NRZ, non-return to zero, to PAM4 was necessary because traditional NRZ reached its practical bandwidth limits around 25 Gbps per lane due to signal integrity issues. PAM4 effectively doubles the data rate per unit of bandwidth, making the jump to terabit speeds possible without having to increase the number of physical lanes 16-fold, which would be physically unwieldy and expensive.